needs no target defect data at all. GPS target the zero-shot region operating with no anomaly samples or defect labels from the target domain. Let me precise about what zero-shot means in this work. Following the zero-shot anomaly detection convention is wing clip, anomaly clip, global clip. A zero-shot here is interpreted as annotation-free and defect label-free. And first, not used in training is anomaly defective image of the target domain, and second, pixel level defect annotation or mask. And last, text prompts describing defect types. And now I said primitive. First, effect-free normal training images and pre-training clip and wide resonant features. And last, general priors from foundation models. The practical value is simple. Normal images are far easier to collect than defective ones, and they are readily available even for brand new product lines. Existing zero-shot methods have two gaps. Gap 1 is text prompt dependence. Wing clip, anomaly clip, and other clip need defect types defined in language in advance, or long number prompts trained separately, unstateable when new defect types appear frequently. A second gap is no localization. Global clip remove text prompts but is limited to image level detection. It cannot localize the spatial extent of anomalies, so this is before root cause analysis on the factory floor. This table summarizes the gap. The text prompt methods can localize, but they must redefine prompt per defect type. Global clip is prompt-free, but image level only. And GPS is the only method that satisfies all three properties. It combines the strengths of both lines of work. This is row for GPS check marks in all three columns. Concretely, this paper delivers four things. First, a unified framework. Integrate global clips prompt-free gating, patch for memory bank localization, and send boundary refinement into one pipeline. Second is 5 evaluation studies. Quantify trade-offs among detection accuracy, localization quality, and computational efficiency. Third is single hyperparameter set. One fixed configuration generalized across all 15 MV-AD categories. No per category tuning required. And last one is deployment guidance. Feature case and per category analysis offers practical considerations for real-world inspections. This is the heart of the top three sequential stages gated for efficiency. Stage 1 is global clip. Dual clip encoder produce a rich 1280 dimensional feature and a self-cyclic autoencoder ensemble gate. Each image has normal or anomalous at the image level decision. Stage 2 is patch cores. Wide resonant multi-scale patches are compared against a normal core set using k-nearest neighbors, producing a core 32 by 32. Stage 3 is SAM. Classic agnostic segments refine the map so anomaly boundaries snap to real object edges, giving a refined map plus boundary boxes. And the gated efficiency, images just normal by stage 1, and its state is independently verifiable and replaceable. Let's go stage by stage. Each input image is encoded by two clip backbones, and the L2 normalized features are concatenated into one rich global descriptor. VIT-B32 provides coarse semantic information at 512 dimensions, and VIT-L14 at 336 resolution provides fine-grained visual detail at 768 dimensions, together a 1280 dimensions feature. If you divide your backbones, so I said combining coarse semantics with fine detail yields a richer representation than either backbone alone, and crucially, it needs no text prompt. You can think of it as looking at the image twice, once for the overall context and once for the fine details. Now, how do we learn the normal versus anomaly boundary with no labels? And an ensemble of 6 autoencoders is trained over 3 cycles with 2 adaptive modules progressively refining the pseudo-labels. The first module ARS is adaptive rejection sampling. It uses an IQR box plot threshold to flag pseudo-anomalies as outliers and exclude them from later training rounds, progressively refine the training set each cycle. And second module is AAW, is adaptive augmented weighting. Assigns learning weights by classifier prediction uncertainty in connecting to positive unlabeled learning to learn the boundary implicitly. With the ensemble trained, here is the score and the gate. The final anomaly score combines the classifier output probability and the normalized reconstruction error weighted by lambda equal to 0.5. The gating threshold tau is set at the 95th percentile of the training anomaly scores. And the gate is the efficiency engines of GPS. It lets normal images bypass the heavy stages. It auto-adapts per category. Tau ranges from 0.791 for tile for 0.898 for wood. And as the ablation will show, it is essential for detection. Stage 2 learns only on the flagged images. While the Resonate 50 extracts multi-scale features from layers 1 to 3, they are unsampled to a 32 by 32 grid concatenated into 1,792 dimensions and randomly projected down to 384 with a fixed state, giving 1,024 patches descriptors. All normal image patch features are collected, then reduced by random core set sampling at 25% to cut memory and computer. Each test patch is scored by mean Euclidean distance to its k equals 3 nearest normal neighbors. The 32 by 32 map is Gaussian smooth and min-max normalized. We verify this choice empirically and it will appear again in the evaluation section. Stage 3 tests the course map and refines it with SEM. The map is upscaled. Then SEM-VIT8 produces class agnostic segments. Each segment is scored at its 75th percentile of anomaly values, which snaps boundaries to object contours while suppressing pixel noise. Thresholding then gives bounding boxes. The result is a clean anomaly map aligned to real object edges with boxes ready for visualization and deployment. But I want to be honest, SEM is a double-edged. On the pro side, cleaner boundaries aligned to real contours, suppress noise, and usable bounding boxes, ideal for visual root cause analysis. On the con side, the 75th percentile averaging can dilute tiny defects and lower pixel AUROC for small anomalies. For later pixel AUROC actually rises from 0.862 to 0.9096 without SEM, and SEM-VIT8 is our main compute bottleneck. Now the experiment. For evaluation, we use MBTech AD about 5,300 high-resolution images across 15 categories with pixel-level ground truth mask. Everything runs in PyTorch on a single A100 using OpenClip Torch Vision Wide ResNet and the official SAM VRTH with one fixed configuration for all categories. We report image level AURC for detection and pixel level AURC for localization. And this key configuration, 6 ensemble models, 3 refined cycles, and K equals 3, 25% corset, and the 95th percentile gate is identical across all 15 categories. Here are the heading numbers. We reached 92.49% mean image AURC and 84.62% mean pixel AURC. And I want to stress this is with a single fixed hyperparameter set across every category, so the generalization comes without any category-specific training. These two numbers are the ones to remember from this talk. Breaking it down revolves on interesting pattern. Breaking it down, texture categories of varies 0.981, image AURC texture anomalies, create unique global feature changes that clip captures very well. Object categories average 0.894 with larger variance. Host changes in items like screw and capture produce feature differences that confuse global detection even on non-anomalous sample. For localization, on carpet and tile do well, but wood, grid, and screw are weaker. The 32 by 30 grid and same segment averaging struggle with long linear defects and heavy pose variation. Here are the qualitative results. For each row, you see the input, the ground truth, our heat map, and the predicted boxes. For carpet and bottle, the same refined boundaries follow the texture, structure, and the circular geometry closure. Segment-aware scoring works on both texture and regular shape, sharp objects. You can see how the predicted boxes follow the actual defect shapes here. And here are the harder cases. I think it's important to show this. First, the heavy pose variation activates the whole object, which stimulates localization. For screw, the heavy pose variation activates the whole object, which stimulates localization. For wood, the long linear scratches are hard for a 32 by 32 grid, so the heatmap only partially covers them. These two failure modes pose variation and long linear defects directly motivate our future work. We ran 5 evaluations on 5 representative categories. One, the global clip gate is essential. Remove it and immediately AURC collapse to 0.5 pure chance in every category. The gate is what actually decides which image contain anomalies. 2 is the gate creates a localization trade-off. Counterintuitively, PAURC is higher without the gate. It scores borderline anomalies as 0, blocking downstream recovery, efficient cost, some localization completeness. 3 is SAM has mixed effects. Dropping SAM raises mean pixel AURC from 0.8027 to 0.871 because segmentation averaging dilutes more defects, but SAM still gives cleaner boundary aware maps. 4 is KNN beats Mahalanobis since multiscale patch features on Gaussian, the non-parametric KNN is more robust. Comparable accuracy at 1.6 times the speed. 5 is the speed accuracy trade-off is configurable. Dropping SAM runs 4.9 times faster with even better pixel metrics. Running global clip only is 11.3. Faster while keeping strong detection and 0.914. So the practical guideline is pick your configuration, the full pipeline for boundary, and our maps no SAM for the best speed across balance. Or global clip only when only detection is needed. Let me give an honest assessment of the limitation. The states are sequentially dependent, so a stage 1 false negative can never be recovered downstream. Same VIT8 is a compute bottleneck, and the fixed 32 by 30 grid limits spatial precision on small or long linear defects. And strictly speaking, we are not fully zero shot, we still use normal training images. These directly shape our future work. Adaptive gating threshold, higher resolution grids, a SAM celebration module, and fully level-free localization. To conclude, is we presented GPS, a unified zero-shot framework that does both detection and localization, 92.49% image AURC, and 84.62% pixel AURC across 15 categories with fixed hyperparameters. It is the only method satisfying all three properties. And the modular design lets you choose for pipeline and OSM or clip only depending on your accuracy and speed needs, making it genuinely deployment ready. That's our work. Thank you very much for my attention.
Thank you for your presentation. So there is some question from the audience. Okay, I was just curious to understand better the zero-shot requirement, because if I understand correctly, if you move from the training domain to a different domain with different pieces to be detected, you need some images of normal pieces, sound pieces. Right?
Yes. Yeah.
How many of these images do you require? At least, how many did you use in your test to move the domain?
Like detailed questions is I'm not fast order, so
Yeah, I know.
if you want the answer, so send the email and first order.
Okay.
Yes.
Okay.
I'm sorry.
No problem.
Okay.
Thank you.
Yes.
So we can.
Sorry, there is no technical assistant in this one.
Yes, she did.
Yeah, so the camera is not working. It's not sharing for the YouTube. Damiano says to check. Sorry. We do you go in here? This one. Okay. Okay. And now to share the second presentation. Where is the second presentation?
It was. What's the second one?
Hmm?
The second presentation.
Neural network Edsley Vira.
Diego.
What you want in the name?
The name of
The presentation.
yeah.
Ed.
Oh, okay.
Okay, so when in the meanwhile they are preparing, we can announce the next presenter. Invite on the stage Ed
This one.
Yes.
Girati. She's presenting the work Neural Network and Gaussian Regression Process Comparison on a Physical Problem. The work is from
I'm going to see if it's working.
Merve Gurbat Kaldag and then Vincent Pankmet. I'm sorry for the pronunciation.
It's okay.
I do my best.
It's okay. So, good afternoon and thank you for joining. My name is Ezgi Kıratlı and I'm from TED University. And today I will talk about the neural networks, Gaussian regression process comparison on a physical problem. And here is my outline. I will start with the introduction, motivation, the problem definition, numerical method, which is the radial basis function RBF. Then I will talk about the machine learning methodology, the results, the discussion, and conclusion. First, I would like to start with the basic definitions. The bioconvection refers to the fluid movement that arises when microorganisms swim in a particular direction, driven by cause such as gravity, magnetic fields, oxygen, or light. The generated density gradients induce convective instability. The nanofluids are created by dispersing nano-sized particles in a base liquid like oil, water, biofluids, or ethylene glycol. Open cavities are the particular interest because they are in many engineering applications, such as solar receivers, heat exchangers, and solar collectors. So the magnetic field can control and stabilize in a flow of exerting the Lorentz force on an electrically conducting field, making it a powerful tool for the regulation by convection. A magnetic source is considered here for the first time in this context, and our goal is to develop the neural network, which is NN, and the Gaussian regression process, which is the GPR, models for the bioconvection flow prediction in an open square cavity under the magnetic source influence. And here is my problem definition. As you can see, we have the open wall, the open unit square cavity, and inside there is the copper water oxidactive bacteria inside. And as you can see, the left wall is the hot wall and the right wall is the cold wall. And at the top, at the bottom, we have the insulted wall. And here is our magnetic source with the directions XMS and YMS. And as I said, they consider the steady state natural convection conditions throughout the study. And here we have the single phase is adopted for the nanofluids according to its physical properties defined by these equations. And here we can see the thermal and the electrical conductivities of the nanofluids. And here we can see the dynamic viscosity of the equations. And here on the right, we can see the table shows the physical the thermophysical properties of water and copper. Here we use in the study we solve 5 fundamental equations that the bioconvection flow and the magnetic source field affect. The first equation is the stream function, followed by the energy equation, the concentration equation, 1D is the bacteria density, and lastly, we have the vorticity equation. And in these equations, the U and the V are the velocity components in X and Y directions, respectively. Here we have on the left side, we have the key dimensionless parameters used in this governing problem. Here we have the Partington number, the Rayleigh number, the bioconvection Rayleigh number, Hartmann number, Peclet and Levi number, and lastly, we have the magnetic number. On the right, we can see the boundary conditions are summarized, and on the top wall, open top wall, the temperature boundary conditions are specified in this form. And up to now, this slide shows the symbols that we used up to this part. And now I want to talk about the numerical part of the study is created out by applying the global radial basis function, which is RBF, method to space derivatives. The RBF functions depending on the radial Euclidean distance function, which is here. And it is between the collocation of xj and yj, and the field points are x and y. So the differentiation matrices of x and y derivatives of the Laplacian are found as the equation, which is number 2. The iterations are terminated in the sum of the relative residuals in the infinitely norm is less than tolerance of 10 to the power minus 5. And a relaxation parameter term, which is in between 0 and 1, is utilized once the vorticity equation is solved. The average Nusselt number, the Sherwood number, and the density of the bacteria along its headed wall of the computed by the equation 3 using the composite Simpson's rule in the uniform grids. And here we describe our machine learning approach. We use 2 regression models for the comparison. First, we have the feed-forward neural network, a simple generalized mathematical expression written as the y hat equal to f, as you can see here in this equation, where w represents the weight function, b represents the bias vector, the f function is the activation function, and x is the input features. And in MATLAB, we use the fitnet for the NN modeling. Now the GPR, which is a Gaussian regression process. In this process, we have the kernel covariance function, which plays a huge significant role here. And the GP function is expressed as here, as you can see, where the mx is the mean function and the k is the kernel covariance function. And in this study, we use ARD, which represents the automatic relevance determination, squared exponential. And as you can see, the k kernel is, here is the explanation of the equation. And in MATLAB, we use the fit GPR. Something, okay. For the GP modeling. And here we have the process and the results. The data set created from the numerical solution result, which is f, is equal to r to the power 7 on an equally spaced points is performed. Here in our data set, we have 2,679 convergent results. We have 6 different inputs. As we mentioned before, the Riley, the bioconvection Riley, Hartman MNF, and XMS, YMS. And here you can see the parameter ranges. And the 3 columns with the output features the average Nusselt, Sherwood, and the density of the bacteria. And in this data set, we use the 80% to 20% chain test split. And in the case of the NN modeling, the hidden layer size is fixed to 50 neurons in each layer. And in both NN and GPR, the Z-score standardization of inputs are given. And here in this table, we have a comparison of the bilayer NN and the GPR with various kernel functions is conducted across random seeds between 20 and 50. And in this study, our target variable is the average Nusselt number, which is quite challenging to predict. When evaluating our models, we focus on stability. A smaller standard deviation means a more robust and consistent model. Looking at the results, our best performance was achieved with the seed 28, dropping the MSE, which is the mean standard error, below 0.001. Overall, the neural networks provide the lowest MSE, while the GPR model also stood out highly robust tool due to its low variability. And here, as you can see in the table, the mean MSE and the best MSE is given by the neural networks. And here we have our prediction and the residual plots. As you can see, both approaches capture the actual data patterns exponentially well. However, there is a major difference between these efficiency. As you can see, the neural network is done under 6 seconds, while the GPR is nearly 106 seconds to model. It took these many seconds. And the major difference, sorry, it was said, okay, sorry. Now we have to ensure these results generalize well to new data. We also log C28 and perform a rigorous five-fold cross-validation, making it a perfectly fair and reliable comparison. And according to this table, the mean MSE across the five-fold shows the generalizability of NN modeling is better than the GPR. And here we have our future importance analysis. We analyze the future importance using a permutation based on the approach, which measures how much the prediction error increases when a specific input is shuffled. Essentially, a high score means that the future is more critical to the model's prediction. As highlighted here in the table, across both GPR and the neural networks method, the bioconvection Rayleigh number consistently emerged as the most dominant and critical parameter for every single output. This indicates that our models are highly sensitive to changes in RB compared to other inputs. And the Rayleigh number is the second most important parameter. And after these analyses, we found out that the MNF has a negligible effect. To conclude, we have both bilayer neural networks and the GPA models are successfully predicted our bioconvection flow characteristics, namely the nusset, the Sherwood, and the density of the bacteria. As listed here, the NN achieves is the clearly winner for the speed and accuracy, achieving the lowest MSE, and in just 6 seconds, alongside the superior generalization in five-fold cross-validation. On the other hand, the GPR stands out as a highly robust alternative due to its low standard deviation, making its prediction incredibly consistent. And physically, for our future importance analysis, that the bioconvection Rayleigh number, RB, is dominant parameter driving all outputs closely by the RA. And looking ahead for our future work, we plan to extend our parameter ranges, test deeper learning architectures, and integrate formal uncertainty quantifications. Here are my references, and thank you for listening.
Thank you for your presentation. There is some questions from, please.
Okay. Yeah, very nice presentation. Interesting about the future importance. It is described that RB is the most important features.
Yes.
And also after that, FA, the second one.
Yes.
How do you define which method that you use for define which is the most important features?
Okay. Here you say we had shuffled 50 future, and let me just. RB is it scales the bouncy force generated by the microorganisms accumulating near to the top boundary. Since bioconvection is instability and boundary, fluid movement are entirely driven by this biological density stratification. It makes the perfect physical sense density. Our models are highly sensitive to RB predicting the heat and the mass transfer. I hope this gives answer to your question. If not, if I understand right, you're asking me how did I find RB is the most important.
Maybe like the selection or something.
Okay, just a minute. It has to be. We analyze future. We essentially high score means the future is more critical models prediction as highlighted in the table across the GPR models. We shuffled it 50 times and by the inputs, the average nusset, Sherwood, and the density, and by doing it here, as you can see, the cross-validation with the lowest MSE, we found that the RB was the most important output of our model. Thank you.
It's okay for you?
The second one?
Yeah.
Okay. As this features using the same distribution, I'm saying before that you described the physical equation with the same distribution, like using the continuous data or something, or binary or discrete.
I couldn't understand the question, sorry.
So A and B, the same distribution, so like using Gaussian. So it's the continuous,
Yes.
or it's discrete, or it's.
We have
Yes.
for our future work, we will work on more inputs, and for this problem, probably the data was not, because we had like 6 different inputs. It would get more complicated for our future work. We are hoping to do more and continue on this data and work it on. I hope I understand your question. I'm sorry.
Is there any other question? Just curiosity. I was wondering, you use 2,000 and more examples.
Yes.
Do you think that by increasing those examples, you are able to improve your performance, or you are reached a plateau, let's say, and that's it? And the second question is, you talk about other neural architecture that you can want to try to use in the future work. If you
Yes.
can give us something about.
Further architecture. Okay, I got it. For the first question, we want to get to the deeper. Like while we started, we didn't know the MNF had a negligible effect. While we were studying, we were working on. We found it more. Probably it will get more complicated, but because of the NN and the because it has like the load time, like nearly 6 seconds. I think in the future work it would have more. How can I explain? I'm sorry. It could get we could get lower MSCs, and the NN model could be more bilayer. And for the second question, you ask are for like the uncertainty quantifications, we are provide a single output value for our future work. We'll utilize the GPR to give us both the prediction and its probably distribution, telling us exactly the model and certain and uncertain in our future work. Did I get it? No. Okay.
Okay, so if there are no other questions, thank you for your presentation.
You're welcome.
We can move on the next work. So I invite on the stage, I think there is Diego Silva Piedra, and he's presenting the work A Light GVM Framework for Operational Tide Forecasting and Predictive Imputation in the Rio de la Plata. Sorry. From Diego, Pablo Ezzatti, and Monica Fossati.
Yeah, maybe it's this one. You click the
That's
button.
okay.
No, it's the other one. It's not the one.
Oh, this is not.
Eh,
Sorry.
no, but you had opened
Oh, okay, okay. It's in the
the right
other.
one, but then closed.
Okay.
Okay. Thank you. Well, I'm Diego Silva Piedra, and I'm presenting a IGBM framework for operational tide forecasting and predictive imputation in the Rio de la Plata. So let me set the stage for this. The Rio de la Plata is a massive estuarine marine system between Uruguay and Argentina. It's actually one of the biggest estuaries in the world. And it has a characteristic of being a microtidal estuary, so it's not dominated by astronomical tide, but more by meteorological tide, river discharge, and atmospheric forcings. So that makes it a little bit difficult to predict. And in that context, we have this tool called Pronoi RPFM, which is an operational system that produces early sea level forecast for the next 72 hours, probably. And it's physics based. It uses a program called Telemac 2D, which solves 2D shallow water equations for the whole estuary on a dedicated high performance computing infrastructure. So importantly, this operative system has accumulated a database since 2017 that is what opens the door to this work. So the two things we want to do here first is to answer if can we compete with that model, with that operative model, or even complement it with a simple machine learning model. And for that objective, we propose two models. The first one is Pronoi LightGBM1, which is based on LightGBM, which is a really light machine learning framework based on decision trees. The first one is a purely autoregressive, so it uses only historical sea levels as inputs. And the second one also adds WRF wind forecast and the Pronoi RPFM sea level forecast itself as inputs. So to evaluate this, we check out the RMS server at different time horizons from 6 to 72 hours at three stations, which you see highlighted there in the map, which are Montevideo, Buenos Aires, and Isla de Flores. And the second objective is to explore this same tool as a tool for predictive imputation, which is basically reconstructing missing data gaps in the tide gauges record. So I'll come back to this objective in the second half of the presentation. So a little bit more on this Pronoi RPFM operational system. So because it's a reference here. In the diagram, we show the full pipeline of how it's working now. It has a database that is fed by measurement data and model forcings, which can be atmospheric, like the one from the NOAA, or oceanic border conditions, or river discharge from upstream rivers that fall into the estuary. And all of that drives the hydrodynamic numerical model, which is the one that uses Telemac in a computational mesh. And that is what produces the 72-hour forecast, which is then published and evaluated. So the engine itself is a finite element bidimensional version of Telemac, which uses a computational mesh of over 70,000 elements with a variable resolution. You can see there the bathymetry and the mesh used to do the calculations. That is actually the smaller mesh we use. You can see the Uruguayan coast, and then it extends out to the Atlantic shelf. So you can see how it could be computationally expensive to predict here. So we bring in this model, which is a gradient boosting decision tree framework developed by Microsoft. and it has a lot of advantages when dealing with big data sets and a lot of years of data, which is exactly what we've got here. And more in detail, this is what the inside structure of the model looks like. You have a bunch of decision trees, which are estimators, 1 up to 10, and you input an X vector of features that you can decide what they are. And then the first tree makes an estimations, and the next one tries to correct that estimations. That is what error propagation means here. Each tree, they are trained sequentially, and each tree tries to correct the previous tree error. So when you add them up, you have a better estimation, finally. So we can choose here for the inputs to be the previous C levels and some generated features for them. That is what the Bernoulli IGBM1 does. So in each tree, you give them the previous C-level records, and then each node make a yes/no question about that, and depending on the answer, you get an estimation. Finally, the estimation will be the next hour C-level prediction. So that means for the model, you only have a one-dimensional output, and if you want a further time horizon, you have to do something about it. So what we did was to make it recursive. So for y of t, we want to predict y of t plus 1, as shown before, and that is used as an input for the next estimation, and so on, until you get the L-hour forecast that you want. So in each step, the inputs for the model are the previous measured water level in a W length pass window. So we have W samples of past values in each case. And in each one of these steps, we have some temporal features inferred from the water levels. So, and some statistical features, for example, a rolling mean or a standard deviation mean. And for the Bernoulli IGBM2, which are the forcings, we also have the wind and the sea level forecast as an input. So on the data sets, this is what the tide gauges record looked like in the 3 stations. There is a vertical offset just for clarity, but we have Montevideo, Buenos Aires, and Isla de Flores, the stations. And you can see there are different lengths, and they have some gaps, so they are not ideal really. So we have to preprocess it, and somehow the model manages with big data gaps. And for the Bernoulli IGBM2, the second model, we also have hourly speed prediction, decomposed into 8 main directions, and the hourly sea level prediction. So in this context, we trained the model, we held out the last year as a test year, so the results you're seeing is a mean of the error in a whole year of testing. And we made an 80-20 temporal split for training and validation. So the results for the first model, which I recall is only autoregressive, only fed with historical sea levels, is what we see in the graph. We have read minus square error against prediction length from 6 to 72 hours. And the first thing we can see is that the error stays within the physics-based model, so that is good. But at each station, we have different behaviors. Another thing we can see is that, as expected, the error grows with time because it's a recursive model, so it's at least coherent. And we also look at the feature importance for this model, which is how important is it is every feature to the model to make a prediction. So every time the trees split, they use one feature to decide the split. We count them, and we here show the top 5 of these feature importance, which are really an intuitive and consistent result. We see that for all 3 stations, the most important feature to predict the next water level is the previous water level, which is really something you'd expect. But then the behavior starts to change. For 2 stations, the most important 2 or 3 features are the water level at 24 or 48 hours before. But for Buenos Aires, the rolling standard deviation and the statistical features start to show up. So that means that the model is catching a station-specific behavior. And that while in Montevideo and Isla Flores, the previous water levels are most important, here the variability of the water level stands out. For the second model, which adds the forecast inputs, we have here the RMS improvement. So this is how much the RMS is reduced in the second model by adding the 3 configurations, which is only wind forecast, only sea level forecast, and adding both. So at short glance, we can see that they are all positive, so it always improves over the first model at every time horizon. And then we can see that adding both, adding the wind forecast and the sea level forecast is consistently better. So actually what this does is to stabilize the error beyond the 12 hours. Moving on to the predictive imputation, as you see, the tide gauges show gaps, show missing data that could arise from sensor failure or transmission error or power outage. And they are really more frequent when water level rises because of storm sources and so on. And then they end up undermining model training and model calibration, really. And we can say that some conventional methods fall short in that. For example, linear interpolation or harmonic reconstruction really ignore the physical forcing that really drives the water levels. Another methods, such as spatial methods, need simultaneous nearby data that we really don't have here. So our idea was to use this same Pronoy-like GBM model and treat gaps as unknown feature or past segment. What I mean is that, unlike forecasting, those gaps have serial observations on both sides. So they have observations before and they have observations after. So we can anchor the construction to each boundary. So we do that following these steps with the shown model. We make first a forward prediction. We predict the gap as usual, but then we reverse the time axis and predict the past using the future, which is a recursive prediction using the post-gap context. And finally, we blend it with a distant weighted sum. So these are the equations, which are really simple. What they mean is with the forward prediction, we give full weight to the nearest boundary, which is the past, and we do the same with the backward prediction. So we have the imputation level to be the forward prediction times the forward weight plus the backward prediction and times the backward weight. So you can see if my step is 0, the full weight goes on the forward prediction and vice versa. This is an example to make it more easy to understand. um, the gap is the shaded area, and you can see the blue dotted line is the forward prediction, the green one is the backward prediction, and the red one is the blend, the weighted blend, which really tracks the observed, the reality, so the observed measurements in the gap, which is the dashed black line. So how do we evaluate this? We follow a protocol inspired by TSI benchmark. We use the same lengths of artificial gaps, 6, 12, 24, 48, and 72 hours on one of the stations of the video. We repeat it several times, and we follow two gaps mechanisms, two types of missing data. The first one is missing completely at random, which means basically that these gaps are independent of the water level itself and from other variables. So just the measurement device shuts down at the time and then it turns on again. That's the kind of gap this is. And then we have missing node at random, where gap positions are biased toward high level water. So this is a little bit more realistic because it represents when there are strong storm surges and sometimes tide gauges go down. So following this evaluation strategy, we also have the RMS error against the gap lengths in hours. And we have the two mechanisms. The red one is missing node at random. The blue one is missing completely at random. And we can see that up to 24 hours, we reconstruct the gaps with less than 10 centimeters of error, which is really a strong performance. But then the error goes up. And interestingly, at the end, they both converge at more or less the same error, about 16 centimeters, which really indicates that finally the most important thing is the gap length and not the kind of missing data that we have there. So to wrap it up, 4 points. First, that we found that Pronui Light GVM, our machine learning model, is a viable complementary tool for operational water level forecasting in this estuary. Second, that external forcing is still the key, which is what makes our model to keep the error stable beyond 12 hours. Third, about the imputation, we could say that with this strategy of bidirectional imputation, we can reconstruct up to 24 hours with less than 10 and 12 centimeters of RMS error. And some words on the future work in this line of investigation. We have to extend this model to all stations and really compare it and benchmark it against the operational Telemac 2D model to see the advantages and disadvantages. Then we'd like to use it with hydrodynamic ensembles as well. That's something we're working on. And finally, integrate it in real time into the Pronui operational system. So that will be all. Thank you for your attention, and I'm moving to questions.
Thank you, Diego, for your presentation. Is there any question on the topic?
Okay, for this presentation. So it's interesting for the processing like imputations. We're also working on some of the methods for the imputations. So as long as I know, as long as I see from the presentation, are you using the like GPM for training data for the following the pattern of the tide sea level? After that, you're using it for the missing imputation using the MN curve, using the backward and forward, and how to define the so for previously that you define that the window that you're using affected from the 6 hours to 72
Yeah.
hours. So how you to define that it's from these informations is follow your previous signal patterns.
I lost you at the last
Okay, so
question.
how do you define that your invitation methods to follow the pattern that from the previous?
Yes.
Yes, because mostly when you do the feature from the methods inputations, sometimes it does not follow the previous one, like
Yeah.
from the good conditions, something like that.
Well, I don't know if I understand it correctly, but just give me why do we use the past?
Yes, it's of course writing maybe.
Because it may not follow the same pattern.
Yeah, something like that.
Well, we trained the model with over 8 years of data, and what it actually learned is how this data normally behave. So what we trust in is that in these gaps, the data will behave in coherence with that learned pattern. I don't know if I'm answering your question or not.
Okay, so it's effective also for moving window. So it's like a static window. So it's effective for moving window.
Well, actually, I don't believe so because if you extend the gap length, this will start to diverge. The prediction of the model will start to rise or go down or stay. Uh, so I don't think it's good for a moving window. Thank you.
Any other question? Okay, thank you, Diego.
Yes.
We move on our fourth presentation. I suppose the presenter is Alexander Koenig. Okay, please get onto the stage. So the work is feature-proof detection and segmentation of point cloud from Alexander Koenig, Ivana Kolingerova, and Thomas Bayer.
What do I need to do now? Oh, thank you. So, okay, good afternoon. My name is Alexander Koenig, and along with my colleagues Ivana Kolingerova and Tomáš Bayer, we worked on the paper titled Feature Curves Detection and Segmentation of Point Clouds. I would start by saying that mostly we are focusing on working with geodata, which are often large point clouds, which are acquired by LiDAR scanning. This means of acquiring this data often introduces some artifacts into the data, such as noise or holes, and we would like to further process these data sets to make them better. They are point clouds, which means that they take less space than meshes, but it often makes them harder to process. We are focusing to reduce the computational cost on dividing the point cloud into distinct subclouds along their most important features. And we are doing this because we want to determine the domains of the subclouds, and we want to separately process each subcloud. For example, I would like to further focus on hole filling in geodata. To reiterate, in our paper, we focused on point cloud segmentation. We will be creating very multiple distinctive subclouds, which will be separated by a connected network of feature curves, and each subcloud will be completely surrounded by these feature curves. The advantage of our method is the combination of the following three features, which are that the method works directly with the point cloud without reconstructing the underlying surface. The feature curves are determined directly from the subclouds, and the output can be projected into 2D, which will simplify further processing, and the domains of the subclouds in 2D will be determined from projecting the feature curves into 2D as well. To sum it up, the input is a 3D point cloud, and the output is a set of almost planar subclouds and a set of feature curves. The algorithm can be divided into the following 5 steps. The first step is point cloud segmentation, which creates the almost planar subclouds. Then the second step is crossing point computation. Crossing point is a point in space where 3 or more subclouds meet. So it's like a junction, for example, here. Then we will compute the borders of each subcloud, and we will interpolate them in the fourth step. And then the last step is called connecting the dots, and it will connect the result from step 2 and 4 to form the network of the feature curves. Now I would like to focus on each step in a little bit more detail. The first step, as I said, is point cloud segmentation. For this, we are using the variational shape approximation algorithm. The sources are here if anyone is interested. It is an iterative algorithm. It outputs a set of subclouds where each subcloud can be approximated well by a plane. Then from these subclouds, we are computing the crossing points. As I said, a crossing point is a point in space where 3 or more subclouds meet. For this, we create a subcloud neighborhood graph. On this graph, we compute the maximal clicks, and each click that has 3 or more members will form at least one crossing point. Now, the third step is border computation. As I said, we are computing the border for each subcloud separately. First, we project the subcloud onto its best fitted plane, and to capture the shape of the subcloud well, we are using alpha shapes. Alpha shape is a set of edges between points where there exists a circle of radius 1 over alpha that has the points on its boundary and does not contain any other point from the set. So 2 examples of alpha shapes can be seen on this figure. Each one is with different parameter alpha, and from this alpha shape, we will be always interested only in the outer part. So for example, for this letter A, we will be interested only in the outer boundary, not the inner hole, to call it. So we compute this alpha shape for each of the subclouds. We will have a set of alpha shapes, and now we need to interpolate for each two neighboring subclouds. We need to interpolate their neighboring parts of their alpha shapes. This will create a set of feature curves, but they do not yet connect because of the interpolation. So, for example, this green and this red subcloud, there is created this line here in between them, but the lines are not connected yet to form the network. That is done in the last step. Here we are combining the crossing points and the feature curves that we created in the previous step. For each feature curve, we find the closest crossing points for each end of the feature curve and connect them to create this nice connected network. So I have demonstrated this, or I've shown you these steps on a simple sphere. Now I would like to show you results for Stanford Bunny data model. As you can see, each subcloud is still pretty planar, and each subcloud is completely surrounded by the feature curves. And something that is more interesting for us because we work with geodata are here results for the LiDAR datasets. This is the St. Helens datasets, which are publicly available here. And here we needed to make a few modifications. For example, because it is not an object, it is not a object. We had to add crossing points around the edges of the data set because it's a tile. And here we need to add crossing points where only two subclouds meet. So like this green one and this yellow one, we need to add crossing point here, even though there are not three subclouds that are meeting. And another specialty here was cases such as the islands that can be seen, for example, here. Island is a subcloud that neighbors basically with only one other subcloud that is located completely with it. So we will need to include the whole alpha shape from this subcloud in the resulting network. Otherwise, it works pretty well, as you can see. The subclouds are planar. The feature curves nicely divide the subclouds. There are here is demonstration how our algorithm works for noisy data. Here is a cube that gets progressively noisier. As you can see, the feature curves get more jagged the more noisy the data is. And the point cloud segmentation can sometimes, for really noisy data, create more subclouds than would be strictly necessary. Unfortunately, there were some artifacts that we ran into during our testing. We can divide them into two groups, missing feature curves and missing crossing points. Both of them boil down to the problem of detecting or establishing neighborhoods in point clouds. For example, here is a missing crossing point because these two subclouds, the yellow and the blue one, are a bit too far apart here at the edge, so they do not neighbor, so the crossing point cannot be detected. Similarly, here is a missing feature curve because if we look in another angle at the data set, again, the two subclouds are too far apart to be detected as neighboring. Fortunately, both of these artifacts can be mitigated by further post-processing of the feature curves. So we didn't run into too much trouble when we want to work further with the data. Here is a graph of the computational time. On the left is an axis that displays the total computation time needed in seconds. It corresponds to the black dots. And on the right is the proportional time that was spent in each step of the algorithm. It corresponds with the columns in the background. And on the x-axis are the data sets that we presented in this talk. And I grouped them into two separate groups. Here is the object data sets, and here is the LiDAR data sets that I shown you because they have similar properties in a way. As you can see, as you can see, the LiDAR data sets spend most time in the crossing point segmentation. This is because the data is more complex. There's more going on, basically. There's more noise, there's more details in the data than, for example, in the sphere that's pretty round and, let's say, boring data set. So the complexity of the data will negatively impact the time needed for the computation. Obviously, the point count will also negatively input the will negatively or rather, the more points there is in the data set, the longer it takes to compute. The more complex the data is, the more time it needs to compute, and the more time is spent in the point count segmentation. And the larger radius is needed for the correct estimation of neighborhoods, the more time will be spent in the crossing point computation, which is the orange second step. So in our future, we would like to focus more on the robustness to noisy input data, which again boils down to the neighborhood detection in point clouds, especially in noisy point clouds. We would like to also focus on some post-processing of the feature curves. As I said, this can mitigate the artifacts that we run into, or maybe we would like smoother feature curves than the ones currently detecting. We would also like to focus on automatic setting of the parameters. There is a parameter for the alpha shape, right? There is a parameter for the radius of the neighborhood. So we would like to develop an automatic way of setting these. We would like to decrease computational time because all of this was implemented sequentially. So there is definitely a lot of space to parallelize. And as I said at the start, I would like to focus more on working with geodata and working on hole filling with geodata. So I would like to use this method for my future work. So this is everything. I would like to thank you for attention. And if you have any questions, please ask.
Thank you. Is there any question? When you add the noise in the cube experiment,
Yes. This one?
this is Gaussian noise that you have the progress.
Yes.
So, have you ever any experience when the noise is not Gaussian and well modelable, but is, for example, a very bad outlier in your point cloud that came out when you make leader acquisition?
Yes. The variational shape approximation algorithm should be a bit robust to like a few outliers. If there is not too many outliers, it will perform fine.
Okay, how much do you remember?
Good question. Unfortunately, I do not remember exactly, but I would like return 10% would be still fine. I don't know.
Okay.
I don't know. Unfortunately, I don't know.
Okay, thank you. Thank you.
Thank you.
So I think we can move on our final presentation from Maria Uniga, Paul Florin Rus, and Alina Elena Sultana. ABC-based melanoma detection in non-dermoscopic RGB imaging.
How can I put it on full? Control L. Control L.
Okay.
Perfect.
Okay. Good afternoon, everyone. My name is Maria Oniga, and today I will present to you our work entitled ABCD-based melanoma detection in non-dermoscopic RGB imaging. The motivation for this work comes from the fact that, unfortunately, melanoma is one of the most aggressive types of skin cancer, and its early detection is crucial for improving patient outcomes and also for treatment. Today, melanoma is diagnosed using a technique called dermoscopy, which is an imaging system that allows the experienced dermatologist to assess these kind of lesions using a specific rule called ABCD. This rule refers practically to four main characteristics, namely asymmetry, border irregularity, color variation, and diameter. However, one of the problems is that this type of technique is used only by experienced dermatologists, and also it needs standardized equipment. Thus, we propose a new framework that can be applied to RGB images acquired with conventional cameras rather than a dermoscope. The problem in this case is that for dermoscopy, we have standardized conditions. So we have polarized light and magnification, and the dermatologist can observe specific features like the pigmented network of the lesion. In the case of standard RGB imaging, the main problem is that we have a lot of variabilities, which are mainly introduced by lighting conditions and also by the fact that we can have reflections due to patient movements, and there is no magnification. To overcome these challenges, we propose the following framework, which starts with the original image that is first pre-processed. We localize the lesion, crop the image, correct the illumination, and also segment in order to obtain a binary mask of the lesion investigated. Then with this pre-processing pipeline, we can move forward to the extraction of the ABCD rule and extract those 4 characteristics, which are then further used in the computation of the total dermatoscopic score. It's a clinical score that can assign lesions according to their risk category to low, medium, and high risk. To achieve this, we use the proprietary dataset that was acquired using the MelanoDET system, which is a multispectral imaging system. Although for this study, we used only the visible spectra. Initially, MelanoDET has also a thermal camera and the near-infrared camera, and here are the LEDs that we use to illuminate the lesion at 940 wavelength. Regarding the acquisition conditions, we place the device at a 40 centimeter distance from the patient. And also, we place a marker around the lesion to be able to localize it and perform the conversion from pixels to millimeters going forward. At the moment that we prepared for this paper, we had 146 lesions in 3 categories. We had 72 benign nevus, 47 dysplastic nevus, and 27 melanoma. For the study, all the patients gave their consent, and we also received an ethics approval from our bioethics subcommittee from the university. Now, to avoid all the variability that was introduced during the acquisition pipeline, we first localized the lesion using a YOLO V8 model, which was trained to detect the reference markers if the lesions are too small and too different in shapes, for which we achieved a mean average precision of 0.98 and an F1 score of 0.947, which says to us that we have a reliable localization, and then we used that for cropping. After this, we performed the illumination correction using 2 methods, gray word normalization to remove the color cast, and then white balancing to be sure that we obtain the real color of the skin since it has red subtones. We did this by scaling the green and blue channels to the red channel. And finally, we obtained a binary mask, which was obtained through manual segmentation because we didn't want to introduce certain segmentation errors. The most important part of this work is the feature extraction step. For the first characteristic, asymmetry, we split the lesion into halves for the horizontal and vertical axis, and then we overlap them and try to measure how much they overlap. According to the literature, if the lesion is really asymmetric, there is a high risk of melanoma. For border irregularity, we proposed an approach that uses 2 complementary measures. First, the deviation of the lesion's contour from the convex hull, and then the radial variation. We computed the distance from the contour to the centroid. Moving forward, we also determined the total number of colors. Mainly a skin lesion has up to 6 distinct colors. And if there is a minimum of 3 present, then we have a higher risk for developing melanoma. And lastly, the diameter, we computed the equivalent diameter from its area and converted it from pixels to millimeters. The most challenging part in the feature extraction pipeline was the color classification. A skin lesion can have, as I said, 6 colors, mainly white, red, light brown, dark brown, blue, gray, and black, whose triplets, RGB triplets, you can see here. The problem is that they do not apply for the data set that we used. And because of this, we needed to find a way to determine the actual RGB triplets for our images, which was performed using k-means quantization. Using the new triplets that we obtained through k-means, we proposed a hybrid model. First, based on RGB basic rule part, which, for example, yes, if red is dominant, then we have red pixels. If red is greater than blue, greater than green, then we have brown, and so on. And if any other pixels were not assigned using this basic rule, we use the distance-based one, in which we compare the value of our pixel with the new references we obtained. The results were pretty amazing in a way that before using this hybrid classification, we never identified the blue-gray regions. And using this hybrid way, we could further identify the blue-gray regions and also obtain higher accuracy for the classification part. Regarding the results of the extracted features, we analyzed the mean values we obtained for each of the 4 features, for each of the 3 classes we analyzed, mainly nevus, dysplastic nevus, and melanoma, which have a specific trend which respects the clinical one. Melanoma will have the highest values for symmetry, border irregularity, color, and diameter, and the lowest values will be for the benign nevus. And we discovered that we also could evaluate the dysplastic nevus class. This is a more specific class because it has an intermediate behavior. It's a gray limit, let's say, and it possesses very specific traits, both to nevus and both to melanoma. We also wanted to go a little bit further and see if the overall classification, let's say, receives good accuracy. For this, we computed the total dermatoscopic score, whose formula you can see in the right part of the slide. The total dermatoscopic score gives us the risk. So we could compare what we obtained with TDS with what was already labeled by dermatologists for our dataset. And we obtained an accuracy of 0.705, specificity of 0.94, and sensitivity of 0.63, which is not good nor terrible. It can still be improved. Because we also wanted to see if we can determine a better threshold for the melanoma branch of the TDS score, we performed also a binary test, melanoma versus non-melanoma, for which we used the UDENS index to determine the best threshold. For us, it was 5.7, which is actually pretty close to the clinical one of 5.75, and also achieved an area under the curve of 0.836, which is better since we are using the binary case. Lastly, we also looked at class-wise results. The best results are obtained for the Nevi class with the most correct identified cases, and unfortunately, the lowest ones were for dysplastic nevus for the reasons I already mentioned before. Every method had strengths and limitations, and I would like to talk a bit about them. In our case, the strengths are, the most important strength is the interpretability. Unlike any other black box approach, someone can get pretty insightful information based on the features that we use. And also, using RGB imaging, we can provide low-cost and accessible melanoma screening where one is not available. The limitations are, of course, the fact that we have a real small data set, and that because we use the manual segmentation method and we analyzed only the RGB modality. So for future work, we would like to overcome these limitations by introducing an automatic segmentation pipeline, obtaining much more data, and also perform multispectral fusion. In conclusion, we showed that the ABCD rule of dermatology can be adapted and can provide meaningful diagnostic trends, and it can support accessible melanoma screening. Thank you for your attention, and I'm looking forward to your questions.
Thank you for your presentation. Is there any question in the audience?
There's this is a very good presentation. Just want to ask about the intensity. I saw from this presentation about the limitation from your RGB problem that you have intensity problem, so you solve it with the key. Let's next from the problem. Okay, you solve it with the key quantizations. So after you using key quantization, what do you get? Because can you more detail about what you get from the key quantization?
We obtained the new centroids for the colors that we proposed. So I gave an interval of specific RGB triplets. And then we determined practically the new RGB values that we can use. So the simplistic example is the blue-gray. If we use dermoscopy, it's polarized light. Blue-gray actually doesn't look like that in a dermoscopic image. Unfortunately, since for us this was not the case, sorry, I keep touching here. Okay, so this is the original image. We can see here, I don't know how well you can see from there, but we can see here that we have certain areas where we have blue-gray. Using k-means, we actually extracted the new values for the blue-gray, which here is an example, but these two were used finally to be able to achieve this.
So maybe in future, because your accuracy is about 70%, about 70%. But you maybe there's not there are so many quantification methods like K-means are there. It might be increase your accuracy using this method.
I only tried k-means quantization, I'm not gonna lie. But we can test it further, yeah.
Thank you.
Any other question? Just one curiosity. If you make a manual segmentation, why do you need YOLO the first step?
We use it, so the original image, I don't think it looks like this.
Mm-hmm.
And we can't really use it this big since this is in accordance with what we obtained with the other camera. So we really need to crop this one to look like the NIR image, for example. And we just use it to detect the reference marker and then cut it so we don't need to do it manually.
Mm. Okay, good. So this was the last presentation. I thank you all for listening to this session. I want to thank you, Kazin, for your support in this session, and I hope you can enjoy the rest of the conference. Good afternoon.
Thank you so much.
Yes, yes, yes. So we have the previous month. We moved every week, so it's not really like a 15. Yeah, you can have the methods. You made yeah, moving with the patient. You make it recursive about some material value side. Yes. How much time? Yes. Yes. So it's like for example, when you have a big group, you might miss when you have a big group. When you know, okay, like this, like this, when you follow this one, you can make it more, more. This yes, and uncertainty is reduced because you have some more. So you can, for example, the first 12 hours, yes, use the last 6 of this operation. Absolutely. Why I'm asking you, but are you training this one to know the no, because I use the same model as I use for prediction, and that model, I remember at time t, to produce the time t plus 1 level, it used a W window, which was a parameter optimized by Tuna, and it depends on the station, but it was more or less 60 hours. So I have to yeah, but maybe that's a line of investigation to reduce the window and make small predictions. Okay, maybe window imputation. I mean, same thing. Roguelike. Okay. Nice. Very cool. That's you're working on a fund. Yes. Very good. Now we should. After you did your PhD in France, or what were the subject? So I was in minutes. So how much? So I'm working to detect the regulation of machines. So I'm also working with the pre-processing methods because I'm using the federations. Like here you're using the types made from the pressure. So I'm using the federations from the XLM. What kind of machine is it? I think in every machines, but I'm concerned for now. I'm using for the machine referring machine, like most of the machine that will rate using the bearing, bearing. Yeah. Yes. So I'm concerned about the bearing. See, studying the sensors of that machine. Yeah. So because you cannot divide this machine in the health condition or non-failure condition. Because you cannot, because actually in the industrial machine it's working 24 hours a day. You can stop it, you cannot detect inside it, so you have to just to predict. And using machine learning for that? Yes, I'm using a stochastic methods in the market. It's ancient methods, it's very great. It's not very familiar because it's more mathematical method. It's mostly for using the coding, yes, but using it's more adaptable for the small devices. Okay. Yes, I'm using the most of yes, I'm using the hidden model and I have to make sure that I reduce the uncertainty first using the processing using completion, preparation for the smoothing process. Okay. Yeah, I really know this one. There are some that can handle using data, like this data union, if you have small gaps in it, you can find a pattern there and say, okay, when using data, maybe there's a pattern and it can learn from it. Okay. But sometimes.
2 more minutes. People are still on the coffee break.
Okay.
So you live in Porto and you study in Cagliari.
No, I studied everything from India. I was working in Cagliari.
Working.
Yes,
Okay.
I was working in University of Cagliari.
Sorry, you look very young. I thought you were a student.
No, I completed my PhD in India. Then I was a postdoc.
Okay.
And then for my second contract, I turned it into remote and I moved to Porto.
I see. I thought they were getting grad students to work as a...
No, I did my graduation 9 years ago. I have a lot of Brazilian friends here.
There's a surprise for me. It's my first time in Braga. I went to Guimarães and Porto several years ago. And when I got Uber here for the first day, the driver was Brazilian. And we started talking Portuguese, but his Portuguese was clearly Brazilian. Then the second day, we got another Uber driver, and he was also Brazilian. The third day, we got another, he was also Brazilian. And he told me that maybe 40% of the city,
Yes,
that's a
we
lot
have
of Brazilians around here.
Brazilians. I think
That's-
5 of my friends are Brazilians.
They're curious. It's a small place.
No, not in Braga.
But Porto?
2 of them live in Guimarães. They're doing a PhD from University of Minho.
Mhm.
And 2 of them live in Lisboa, and 1 lives in Porto.
Good Brazilians, I hope.
Yeah, they all are very close friends.
Okay. Well, I think we should start with what we have.
yes.
Okay, people, good afternoon. This is the general track. Are we muted?
No, we are unmute.
Okay. The general track 5A3 from ICCSA 2026. I'd like to welcome you. Are you going to present?
No.
Okay.
I think he will present first.
He's going to present. What we are going to do is that we don't have the first presenter yet. So it's Leonardo. Leopoldo, sorry, I can't read the very tiny letters. Then Leopoldo and Ana. Then we're going to shift. Then if Abdel Hamid comes, we can change the order. I think it's okay. So Leopoldo, I'd like to invite you to do your presentation now, if it's okay.
Let's share the screen. Okay.
They see the video, right?
Yes, but why am I not able to? Okay.
Okay. Thank you. So
Okay, why does it not? 1 second. Duplicate. Okay.
Yes. No.
it's showing
You
here.
have to change it.
Yeah, and
We have synchronized with the camera.
All right.
That's-
It is fantastic. No.
I will just share the screen. Perfect.
Ready?
Ready?
Okay. Thank you very much.
Thank you.
The first presentation is going to be a laboratory test bed for benchmarking orchestration logic in collaborative digital twin environments.
Yes.
That from Leopoldo Silva. Leopoldo, thank you very much for your collaboration. You have 15 minutes, but we are not going to rush you too much.
Okay, don't worry.
Please go ahead.
It should be enough. Okay, good evening, everyone, and thank you for attending. So I'm going to present a paper which is titled A Laboratory Test Bed for Benchmarking Orchestration Logic in Collaborative Digital Twin Environments. It is a very nice title to a relatively simple word. Let me see if this works. No, yes, no, no. You can please.
If you can just say I can change it.
Okay, so this project of the work I'm presenting is integrated in a global project that is running in Portugal, in particular the Prototech, where we have the goal on the project as the goal to benchmark several production planning algorithms to the industry in diverse scenarios and using different operational philosophies. In particular, the partners wanted to test collaborative planning and concurrent planning, following a modular approach and whichever goals the project has that are always very ambitious. And so we, as a research and technology center, we're trying to experiment with these algorithms. You can advance, please. And so here we face, I believe, the usual problems that the research and technological centers face, and even the universities. That is, when the project starts, we need data. In particularly, we need enterprise data, real data from the enterprise partners to start our research and then to present the results, all in the project time. So this is always our goal, at least our initial goal, and everything is planned. But then what really happens is that there is no data. We are 6 months in the project and there is no data. We are 1 year in the project and there is no data. And then suddenly, more or less, when the project is getting over, some data appears, and then we have to do our research in a very short span of time and present some results many times already out of the project timeline. I believe this is very common with the work we do. I do believe that this is not the enterprise fault. Many times this is how the projects are done and how they are planned. And so the enterprise themselves many times don't have the maturity they need to have when the project starts to fulfill the project goals. You can advance. Rafael, right?
Sure. Rafael.
Yeah. So, and this is something that is very common today, that is a scenario of what could happen or what can happen. And it turned to be our goal in this project. And the thing is, if we don't have data, we can simulate that data. We can create an alternative reality, if you wish, of the enterprise and start doing our research at the project beginning without waiting for the real data. So I do believe that we all have this goal also to start doing our work, in this case to explore planning algorithms, without the need of having the real data. So our goal in this work and in this paper was to build this simulation tool and generate the synthetic data that would allow us to start our research. Don't advance here, please. We also believe that this decoupling of dependencies facilitates and enables faster research and even technology transfer to the market. Because as a research and technological center, we are not transferring technology directly to the enterprises. We are transferring the technology to software houses. So we have this third partner on the loop that we transfer our technology and our findings, and those are the ones that need to implement it in the project timeline. So we do believe that what we are trying to achieve here is very valuable for this type of projects. You can advance, Rafael. So anyway, in this project scope, we started by defining a three-layer architecture. We are using FiWare as a technology base. It was chosen by the consortium, and NGSE linked data as a way to describe data. And so we have this technological base we have to use, and it is a good base. But then we did this architectural where we try to build the digital twins of the organizations, of the enterprises. And so these are a digital view of what is the enterprise software that is on the ground, on the shop floors and on the enterprises. And then we would also digitize the requests. These have several names in the real world, from orders to production orders, if we are on the shop floor, and several other names. It depends on the application. And then we will build on the service layer and try on the service layer our algorithms. So these are all simulations. These are all simulations in our solution. We are creating this alternative reality to try our algorithms that we will then give to the technological partners so they can implement them. And one of our goals to build this architecture was to replicate a similar setup, much like what is used by these technological partners. You can advance a bit. Advance it, please. Now, this is the request data model we are using. And I believe this is one of the breakthroughs we've done in this work, in this particular work I am presenting here. Because this represents a request, so we have ecosystems of participants in our simulation. This can be customers of enterprises, so we have the customer, the enterprise. These are the participants of the ecosystem and the simulation. But if we look here, whenever a participant wants something, he will send a request to the system, and several of the fields of this request, of this data, are responsible for them is the participant. And then from another fields, like when the request will start to be produced and when I plan to end it, is from the planner. And then when it actually started to be producing and when it ended to be produced, is from the responsibility of the producer. And also this request as a state, it started by being pending and allocated, and it is in production. Finally, it is completed and then delivered. And this status is maintained by all of these guys. These ones, when it creates the request, set the status as pending. Then the planner sets the status as allocated, and so on and so on. You can move ahead, Rafael. So our experimental methodology was design and science research, so an interactive methodology where we try to develop an artifact, in this case, the co-simulation. And these papers only presents the first interaction, as we will see in the results, actually. And so in the simulation, we had a small ecosystem, only with 15 active nodes or participants. Some were producers and other consumers. And we used or implemented a quite simple planning algorithm that we call it first come, first served, and which sequential diagram is represented here. So a consumer wants something, he will create a request, on the Orion broker. This is a technical piece from Fireware. Orion broker actually keeps the digital representation of the request in this case. And so the consumer starts by creating the request in the Orion broker with the status pending, and the broker notifies the planner. It tells the planner there is a new request here that is in status pending, and the planner allocates it or sets the status to allocated and sets the allocated to field to another participant that will receive this notification, will get the request, will start producing, notify the consumer that the production was started. And so as it produces the order, will update the quantity that is already produced. And in the end, the request is status is set as completed. You can advance, Rafael. Okay, and so on this setup, on this simulation, we did 4 initial experiments, mainly to check if the architecture was good enough to keep going. So we did not explore on this paper scope another algorithms. We are just checking if this architecture is good enough to keep going. And so on the experiment 1, we are focusing on latency and on responsiveness. We are measuring the time between the moment a request is created and the moment the consumer receives a notification. So we are measuring the request creation, the planning of the request, and then the notification that the request was allocated. And we have a mean latency of 10 milliseconds, which is not too obvious why. We know that logic execution of the planner takes about 2 milliseconds, but we did not study further where the other 8 milliseconds are. Of course, it is on network latency and brokers processing. And then on experiment 2, we tried the same system under network load. So we launched the 15 participants making 100 concurrent requests. And our question here was, are we going to lose requests? If we overload the network, is Fireware able to not maintain all the requests and notify the participants of the allocation? And our conclusion was that yes, it can. So it processes every request with an average throughput of 75 requests per minute and with a transition success rate of 100%. Please, Rafael. And then on experiment 3, we are checking if the local states, so each of these components, participants, has its own state regarding the orders. And here the question was, are these states synchronized? So I have several states of the system that should be the same. Are they really the same? And our conclusion was that yes, they are, with a latency of 8 milliseconds as a mean. So we know that for 8 milliseconds there could be states that are not synchronized. We don't consider that, at least till now, we don't consider that has any significant consequences. And finally, on experiment 4, we wanted to try the system. The question was, is the system able to recover if the planner fails? So if I start failing participants, in particular the planner, is the system able to keep all the requests alive? And so is the system reliable? And our conclusion was again that yes, the system is able to recover from failures, and we have a data consistency post-recovery of 100%. Please, Rafael. So here is the thing. In this paper and on the scope of this paper, we actually did not explore the algorithms that we wanted to in the project scope. We are doing that on another projects, and we are still exploring this co-simulation, but we do believe that we built a stable enough architecture to keep exploring. Please, Rafael.
Oh, sorry.
And so, in the future, we want first to scale up. We want to try this with thousands of participants, hundreds first. Actually, that is something we are trying to do now. It involves developing the code, the simulators, using another techniques. And then, yes, try new heuristics and algorithms for production planning, in particular concurrent and collaborative planning. And then extend the data models. We are only right now using the request data model and the participant data model, but we want to try production planning data models and other data models that can enable and extend our work. And finally, we want to do dynamic replanning. That is, if a new participant arrives in the system and we are doing collaborative planning, we want to readapt on the fly the planning that is done and the allocation of the orders to have this in consideration. So the new participants in the systems and even old participants that have left the system. And I guess that is all. You can, one more, please.
One more?
Yeah.
Okay.
So I am Leopoldo Silva. I am a senior researcher at Center for Computers Graphics in Guimarães. We are based in the University of Minho, but on Azureiro campus, and everyone is welcome to come visit us, and we'll be very glad. So, questions, please.
Thank you, Leopoldo. Questions? I always have questions.
Yeah, sure.
And I'm going to point that to the slide because that's the part that got me very curious. That's the one. Yeah, so you're simulated, I said that the fragmented manufacturing hub.
Yeah.
Fragmented in the sense of it's separate units not communicating or not optimized.
No. The application ecosystem is diverse. The only central piece in this ecosystem right now is the Orion broker. Because every consumer, if we are talking about an enterprise, has their own ERP or whatever, management software. And what we are actually trying to do is to synchronize these pieces. So whenever I want to produce something and need to subcontract this production, and so I am making a request that will be made by many companies, and let's say that this is collaborative planning, I need to have a view of the current state of this request. And however, this request lives in many software applications, and it is there is not many solutions that are able to synchronize them and keep a consistent state. And so that's why we call it, yes, fragmented.
Okay, fragmented, I was thinking about it, if it is fragmented because it could be optimized on the sense of it's so messy, but it's not. It's fragmented because it is distributed.
Yeah.
That's its nature. That's not something that you need to solve. And that takes me to the next stop me if you want.
Yeah.
That takes me to the next section. That they said something very interesting here. New heuristics and modular interchangeability. So you have this fragmented by nature system that you're going to orchestrate the send information, get information, try to get a sense, and eventually try to optimize the production of this distributed environment. Are there constraints, for example, that you cannot cross them when you try to optimize, or anything goes?
No. Actually, there are many constraints, but we are looking at the business logic of every enterprise is different. In particular, the machine state that regulates the request of every enterprise is different. So they have preconditions and post-conditions that are actually different, but we know something, that once an enterprise says, I completed this request, it is completed. So I don't really care about these differences. You see, from a global viewpoint, I only care that I can make the systems progress. But that is true. That there are too many challenges if I start to go into detail related to the state, and mainly to the state. That if you go to the other slide from the data model, that state, that is the challenging bit, because that has to do with business logic that is different from enterprise and participant.
But having many constraints make the work easier or harder to orchestrate the
I do believe it makes it harder.
harder?
And it is not having many constraints, it's having different constraints from system to system. Because we have theory that works very well, but then in practice, the applications that are running in the factories and the retailers, they are all different, and they are, even if they are from the same software house, they are parameterized or configured in different ways. And this actually makes the constraints different. So this constraint set may be small or not very large, but their difference are the big challenge.
I see.
Yeah.
Oh, that's a very interesting task that you have ahead of you. So thank you very much.
Thank you.
And I'd like to see why we didn't. Just a second. Delmahid is not here. Lamia or Mohammed, are they online? Can you check it for me? Just to make sure that it should be in person, but let's see if they're online.
No,
That's there's giant.
no.
Okay, in this case, I'd like to call Ana Januário to present her paper. Okay.
It's about evaluating multi-objective evolution.
I can introduce you. Ana Januário is going to tell us about evaluation multi-objective evolutionary algorithms for fairness-aware decision tree turning. Thank you very much, Ana. Please go ahead. You have 15 minutes, but you're not going to push you.
Thank you. This is a joint work with Professor Maria João Alves and Carlos Angela Antunes from University of Columbia.
I can do. Just let me know.
There has been a growing interest in the social impacts of machine learning systems, and including research in topics such as fairness. And fairness affects high-stakes decisions in different sectors, as healthcare, credit scoring, education, but fairness don't have a universal definition. And beyond this difficulty of a definition and put it in mathematics way, the fairness problems in literature appears to be addressed at different stages of the modeling pipeline. Sometimes dealing with training data, and sometimes dealing with the model output and try to balance the outputs to understand how fairness in that model is be treated. Beyond this, the same data set can have fair or unfair results depending on the data set, the fairness definitions, and the machine learning model that was chosen. And when we consider fairness as a optimization, as a objective function in optimization problems, often it leads to Pareto-dominated decisions. So it's hard to deal with this metric. So in this work, we investigated fairness within a multi-objective hyperparameter framework for decision trees. And we aim to analyze how different hyperparameter configurations affect the trade-off between predictive accuracy and the fairness in decision tree models. I don't know if...
Oh,
So we deal with tuning in decision tree models, and why we chose decision tree, because for this use case, we are using healthcare data to predict heart disease. So my final model should be interpretable and should be explainable for that to be validated for a doctor. So we optimize three hyperparameters: the maximum tree depth with search space with integer values from 1 to 20, minimum number of samples to split a node with integer values from 2 to 50, and maximum number of features considered for each node split with search space with integer values from 1 to 7. To explore our Pareto front, we compare exhaustive grid search with two algorithms, evolutionary algorithms, the non-dominated sorting genetic algorithm 2, NSGA2, and another multi-objective evolutionary algorithm based on decomposition. And our objective functions, so we deal with the prediction. So we don't use accuracy because in this data set we have unbalanced data. And we use a strategy using weight to try to balance our classes, but we think it should better we use another metric that don't avoid accuracy. So we use F1 score metric, which is a harmonic mean between precision and recall. And in minimization, we use 1 minus F1 score to have our classification error. As a second objective is we consider as fairness, unfairness in this case, the equal opportunity criterion, which is given by the recall, the difference recall between groups. In this data set, we consider the gender as a protected group. So we measured the true positive rates between men and women. Okay. So the methodology that we follow was we split our data set with three in training, validation, and test set, mutually exclusive. And we consider that the best models that we can have will be on our Pareto front. So we train in the exhaustive research, we train all configurations, all hyperparameters configurations possible, and we delimited all our Pareto front. Then we get these models of the Pareto front and submitted on a test set, an independent test set, to access the generalization results. So we analyze how the values from validation set and test set behavior and pass one from other. We rank the top 5 models by area on the Hawk curve, which is common when deal with machine learning models. To classification, we use the seed operator curve as a way to validate if our model is a good model. And we get the highest value of our model per method and analyze the confusion metrics to see the positive, false positive, and true positive, and check the results. So that's why that is our methodology. Eh.
Speak in white space, I think. Yeah. No, don't worry.
Sorry.
I'm not sure also what I'm doing, but let's treat that. Okay.
So our data set, we use a data set that is available on Kaggle to apply our methodology. As I said, this data set have an imbalance with 91.5% of negative instance and 8.5% of positive instance. This is why we used a balance strategy and also choose for F1 score instead of accuracy. About the optimization, the grid search, the user-strip grid search, each combination of hyperparameter is a model to be tested. So we tested more than 6,000 of distinct models to compute our Pareto front. And we tested these two evolutionary algorithms to see how they behave, how can behavior and trade-off limits of accuracy and fairness. Both evolutionary algorithms were configured with identical parameter settings, with population size equal 50 and over 60 generations. And all test was in Python. We used scikit-learn to build the model, the decision tree model, and PyMo as a framework for optimization. So this is our result. We evaluated more than 6,000 candidate models with 3 hyperparameter settings. Here we got 15 points in non-dominated solutions, which is 15 models that is our Pareto front. We also notice competition between the objectives, where when we have lower unfairness, we have a greater error, as we can see in point G15, and when we get when we get a lower error, we get a higher unfairness, as we can see in point G1. So we check here some competition between the objective, which is some cases normal during the optimization.
Yep, let me try that.
Yep.
Oh,
Control N. Control N.
N.
Control.
No, Control N.
Control and N. N for London.
I have no idea. What's this?
London. L for London. Just
Control L.
yes.
Okay. What's the slide?
Yes, thank you. So for our evolutionary algorithm, among the evolutionary algorithm, the decomposition method evaluated over 3,000 candidate models, and we have for this one 10 non-dominated solution points. NSGA2 evaluated 3,000 candidate models with 15 non-dominated solution points.
when we examine the Pareto front, yes, in the test set, we notice a different behavior here. Because when we see the error in grid search and in the evolutionary algorithm, the error in validation and test are closer, they are closer, but sometimes even the error is low in the test than the validation, and it's equal in three methods. But when we analyze the unfairness, values that are very close to zero jumped to values close to 0.09 to almost 0.20, which may suggest that this metric suffer with the shift in the distribution, in data distribution. If I have a different test set, different data and different data distribution, the metric don't work well. When we analyze the rock curve, considering the grid search, which was the exhaustive search, the best performing model achieved an ALC of 81%. When we check the different, the hyperparameters, they are very different between them. When we observe this model with the hyperparameter shows that lead to highest ALC value, we see this result, final result, as a confusion matrix. This confusion matrix show for us that I recall for men is 82%, the recall for women is 72%, which means that we have same differences between the results, and we also saw that the false positive values for men is lower than the women, and false positive values is higher for men when considered with women, and false negative values for women is higher than men. What this means that men receive more positive diagnoses that have a heart disease and need to do more exams, and in the end they don't have disease. And women, they are classified as healthy, but in the end has disease. So this is why it's important to balance this type of problem. When comparing to evolutionary methods, the decomposition method achieved an ALC of 8%, very close to the grid search. Here we have a recall more balanced than the grid search, because we have a recall for men of 82% and for women 78%, and also false positives and false negatives is closer than we saw on the exhaustive grid search. One curiosity that I can't say here, but I think it's better later, but I will say now, is that this result, this model that we got here, is in a general picture, is a dominated solution, but have the best balance between the models. Then SGA2 give us the shallow tree that we got in this result, but also achieved the lower ALC of 75%. And we have a good recall when considering only recall, we have 90% of recall for men and 80% recall for women. However, we have a jump in false positives and false negative rates. So it's a good recall, but it's not useful. When we consider the objective space of the non-dominated solutions, we got that the lowest error we get by grid search, the lowest unfairness we get by NSGA2, maybe because of this space of exploration in search space of NSGA2. The algorithm explore more the unfairness side. That's why maybe the accuracy was, or F1 score was so bad. But the decomposition method occupied the intermediate region, what means that maybe it's the more balanced result. So, in conclusion, the exhaustive grid search in practice is almost never applied. Here, we use it as a way to understand which is really a Pareto front and which will be a dominated solution. So that's why we commonly use meta-heuristics method to deal with this type of problem of optimization, hyperparameter optimization. Fairness here does not generalize it from validation to test set. So maybe can indicate that it could be that equal opportunity, that was our definition, maybe is a weak definition. Probably we can work with another metric, or this data set has some data drift shift in the distribution that affect our results. So that's why we, in future work, we will try to validate our framework with with others data set, and also include this framework to explore fairness using other types of machine learning models. About the comparison, the decomposition method outperforms the NSGA2 method in explore the Pareto front. In this case, but here it's important also to understand why this method outperforms the NSGA2. So it is a work in progress. Thank you.
Okay. Thank you. Questions?
I have two questions. Before, thank you for your presentations. It was very interesting. Why did you start with decision tree? I know it's the most model that we use. We can describe it. We can explain it.
Mm-hmm.
Yes. Maybe this is.
Yes. We started by decision trees because in future work we want to increment more trees to handle forest and to light boost and goes to others machine learning models that use a tree. And because in some part of this study we intend to validate our final model output with a medical group to validate this. This makes sense. This model here, nah. So that's why we intend to validate this in practice in the future.
Or moving to more confidence.
Yes.
Can I ask the second question?
Sure.
For the data set, it was interesting to show the record difference between women and men. Maybe is it because the data set is unbalanced data? Do you know which percentage of data collected there are in the data set?
We in this work I try to balance using weight strategy, and in the future work is which I already done, so I can talk. I think I used another strategy which we call SMOTE, which is a strategy using simulation, and in both cases we have this kind of disbalance and balance between the genders. And also, in both cases, we also saw that the unfairness did not generalize well when passed to validation to test. Again, the validation values jumped.
So even with balanced data, it's not.
No. That's why we want to use this framework in other data. We already got another data set, but so I want to try if these values is because of the metric or these values is because of the data. So now test this phase.
Thank you very much.
Thank you very much. Oh, go ahead.
I'm sorry, Anna, right?
Yes.
Yeah. Because I may have not understand your work that well, okay? And I am not a machine learning specialist. However, I have a question. Would it be relevant to train the model only for men, do two models, and then to check the accuracy or the F1 score for each model as a baseline? Because I think you are assuming that the same model, the same model is able to answer the question and so have fairness. As far as I understood, fairness is related to the correct answer given when someone is a male or someone is a woman, right?
Yeah, yes, this definition was.
But then I do believe that we have a baseline. That will be the models trained with the men data set and the woman data set, what kind of accuracy the three will have. And that might be a good baseline.
I saw some working using this strategy, but this work, for example, this is the most common definition of fairness. There is more, and there is more difficulty. For example, if we add another layer in this definition, we can see that, for example, in images, for images in skin, darker skin have more false positives or false negatives than white skin. So if I put a layer of ethnic race, I think I can say race, for black woman and white woman and black man and white man, this becomes to train 6 or 7 or 8 models.
Yes. Okay, thank you.
Thank you. Can you help me see the?
Yes.
I think we are not going to have the presentation from Abdelhamid, Lamia, and Mohammed. I'm not sure they're here, but online.
This is over. We can stop sharing.
Okay.
Now this.
This is Jayakant. Jayakant, can you hear us?
Hello.
Oh, hi.
Hi, how are you?
Great, Jayakant. Thank you very much for your questions on this session. Uh, I'm not sure we are going to have another presentation that's going to be before you or yours. So if it's okay, let's start with your presentation. Can you share your screen with us?
Okay, sure. Wait a second. Okay.
Can you make it a full screen? We are
Yeah, sure. I will make it.
great.
Okay.
Ready?
Okay, so let me start my presentation.
Okay. A quick introduction. Dr. Jayakant Kunhot is going to present us GAZE MIL, Attention-Based Multiple Instance Learning for Interpretable Dyslexia Detection from Multitask Eye Tracking Data. So, Dr. Jayakant, you have 15 minutes, but I'm not going to rush you. Please start when you're ready.
Okay, thank you so much. Hi, good evening, everyone. Myself, Dr. Jagan from Kadu University, Department of Computer Science and Engineering. And now I am here to give a brief presentation about one of our work related to uh, screening of dyslexia using eye tracking data and machine learning. So this work is particularly about gaze multiple instance learning, where we developed a framework for attention-based framework for interpretable dyslexia detection from multitask eye tracking data. So let me just go through the background and motivation, like what is dyslexia and why the early screening matters and what the eye tracking data will provide and how the machine learning will help for us for the preliminary screening. So dyslexia is a condition where a child finds it's hard to read even though they are smart and go to school regularly. So if it is not caught early, it can increase the risk of academic underachievement as well as emotional distress. So eye tracking act as a window. So it records how the eyes moves while reading, and it is a safe, non-invasive, and it will give us the view into the cognitive process of reading. It captures fixation, saccades, and regressions. So machine learning can use this data to screen children automatically. So for a preliminary skin screening application. Okay, when it comes to the literature, earlier works used simple handcrafted features like average fixation, duration, and other global statistics features, handcrafted features, fixation, and saccade features with the shallow models such as random forest support vector machines. Then later deep learning models improved the accuracy, but they still looked into one reading task at a time. They tried to represent the fixation, eye fixation as an images and applied CNN. Also, LSTM based algorithms are applied to the raw gaze trajectory as they consider it as a sequence. And for the explainability part, they relied on the post hoc explainability such as the GradCam approaches. Then later, the recent works are focused on multitask data as well as LLM-based approaches are introduced, where they used zero-shot learning, zero-shot learning, or zero-shot learning to extract the features, oculomotor features from the raw eye tracking data and feed into traditional machine learning algorithms. However, no prior work has combined all these things, such as focusing on the fixation level modeling, as well as combining multiple tasks and built-in interpretability or intrinsic interpretability. The main gaps in the literature or problems in the literature is the loss of fine-grained structures, because most of the traditional machine learning based algorithms based approaches, they focused on aggregating these raw data to generate the statistical features. So maybe in case of the eye tracking data, a single long fixation on a complex word carries different diagnostic value than one caused by the distraction. But when they are aggregated, they may look both identical. Then second one is about the single task evaluation. Most method only use one reading task, but a different task reveal different things. Reading a real story and reading a no nonsense words test completely different brain process. Then third is about the lack of intrinsic interpretability. So methods such as GradCam, they just explain the decision after the model is done. So it is just an approximation, not what model actually used, and none will tell you which specific word has model focused on, or which specific fixation has model has focused to give the decision. So we came up with a solution named Gaze Multiple Instance Learning. So it has 4 steps. So we consider in the first step, we consider each reading session becomes a collection of individual fixation events. So we can call it as a bag. So a bag will contains multiple fixation for a reading session, and each fixation is described by 10 10 features. I will explain in the future slides. So it will cover the position, duration, eye movement, where on the page the child was looking, etc. Then for each task we added a task specific APMIL. It's like attention based multiple instance learning MLP model, which will look each instance and give the attention or the focus on which instance is more important. So the neural network with gated attention learns which fixation matter most for the classifying dyslexia separately for each reading task. Then these results from each task are further combined, and final decision is made using another MLP classifier. So this task-specific AppMill can provide intrinsic explainability because they comes directly with the attention weights from the model, and we can map them back to the words on the pages. So we don't need an extra explanation. We can see from the results like in which words are important for making the prediction for a certain subject. Let me go a little bit detail into the technical overview of the multiple instance learning. I already mentioned about each reading trial will be considered as a bag of fixation instance, and each fixation is like a one instance, but for one instance there is no label. We have only subject level label, either dyslexic or typically developing, and no instance level annotation is required, and we may have like 100 to 150 fixations per bag. It depends on each subject, and these are the 10 feature vectors we have extracted per feature per fixation. About it, they are like a gaze position, fixation duration, saccade amplitude and velocity, regression indicator, then light and word position, then also fixation dispersion. Then we introduced, we adopted the gated attention mechanism. It is a popular approach introduced for multiple instance learning in 2018. So in this case, the gated attention mechanism give a fixation, each fixation a score. High score means model found it most useful for the diagnosis decision, and it uses 2 branches, one that highlights the important fixation and one that suppresses less useful one. So this makes it more precise than standard attention. Then in the later we just combine the 3 task specific results for the final result. To evaluate our proposed approach, we have taken a publicly available data set called ETDD70 data set. It consists of eye tracking data collected from 70 participants, and the age range of participants are 9 to 10. They are like Czech. The students are from Czech Republic. Then they have conducted 3 reading tasks. All the tasks are cognitively distinct. One is syllable reading, another one is a meaningful text reading, and another one is pseudo text reading. All 3 tasks captures different aspects of the reading cognitive process. Then we followed a 5-fold stratified subject level cross validation in order to make sure that there is no data leakage. And also we followed the same evaluation protocol as other works, state of the art works done in the literature. Then we evaluated our approach using three metrics, mainly accuracy, sensitivity, and specificity. Also, we have introduced a new metrics uh, called entropy. In the specific case, entropy, it's more about the Shannon entropy of attention. It will quantify reading regularity, how much regular is each subject's reading. We introduced that one. So let's get into the results. So here we have evaluated the performance of our gaze mill framework for each task separately as well as the combination of tasks. So here you can see the best performing single task is for meaningful text reading. Task 2, it achieves an accuracy of 78.6 and sensitivity of 82.9. When the tasks are combined, like when the task 2 and task 3 are combined, the accuracy has improved to 90 percentage plus or minus 5.7 and sensitivity of 88.6 plus or minus 7. So in this case, the T2 is a meaningful text. So it tests how well a child reads a real story. So it involves understanding words, grammar, meaning, and all at once. But T3 test only sound-based decoding with no meaning to help, because the task 3 is about pseudo word reading. But when they are combined, it has improved the. So since each task captures the different aspects of reading, the multitask has improved to an extent. However, we have noted that when the first task is combined with the second and third task, it has made the results more worse. Maybe the first task is about um reading the syllables provided in a grid layout. So maybe the grid layout causes a completely different eye movement pattern that confuses the model when they are combined with the fixation from other two tasks. But more analysis is required with different data sets to finalize this conclusion. Since we have just since our methodology is based on attention based multiple instance learning, and where we have included the gated attention, we just compared other aggregation approaches. In multiple instance learning, there are different aggregation approaches such as mean pooling, max pooling, and standard attention. So we just evaluated the performance for each task data using mean pool and max pool and attention, like an ablation study. So here you can see when the maximum results we have achieved is like 82.9 when we used attention with the task 1 and task 4. But however, our gated attention has provided a result of 90.0 and sensitivity of 88.6. So that's why the gated attention is more relevant here, because gated attention can find out which fix for each fixation, how whether this directs to the diagnosis of dyslexia or to the typically developing, and as well as it can provide how much relevant is each fixation also. Then we compared the performance of our gaze mill framework with the state of the art approaches. So here you can see the other state of the art approaches are the first three tasks are first three works are based on a single task, but they have extracted 400 plus aggregated features and used a multi-layer perceptron for the classification. They have achieved a results between 88.57 to 91.43. However, our approach also has reached almost similar result. But the advantage is we use only 10 features per fixation compared to the 400 features, aggregated 400 features. And we included the multitask fusion, as well as we have intrinsic fixation level attention interpretability that no compared methods provides, compared to other methods such as ResNet, which has evaluated on the image representation of the fixation, or other LLM based few shot approaches have achieved only 80 to 85 for 85.7 percentage accuracy. And this is about the explainability attention map. So since our framework is based on the attention based multiple instance learning, it can provide the intrinsic attention. This heat map shows like which fixation contributed most to the model decision, not where the children look, but the fixation were most useful for the classification. For the typical readers, the model focus on the first word of each line and the later lines. You can see here first lines and the later lines broadly. So maybe it's because fluent readers have consistent reading rhythm. They can land confidently at the start of the each new line and maintain the momentum all the way to the end. So this consistency can be a strong signal for the typical reading. So that is why the initial fixation in each line is selected or have focused more for the decision of typically developing category. And when it comes to the dyslexic category, the model focus on isolated hotspot at a specific word position. So this reflects the heterogeneous nature of dyslexia because each child will have struggle differently at different words. So this is just for the average of all the dyslexic subject. So that's why no consistent rhythm emerges, just individual spots where each child got stuck. We have to examine for each subject separately. However, the typical readers have a common fluent pattern. Then this is about the for the pseudo text reading, where the in the pseudo text reading task where our model has focused. So here you can see like the in for the dyslexia typically developing and dyslexia cases, they have focused on the fifth to seventh line of words, later line. So it's the same region for both, because pseudo text is the text with they are the words with no meaning. So it will be usually harder for everyone initially. No meaning to help, every word must be decoded sound by sound. So that's why early fixation looks similar for both groups. So model does not find them useful. But by later lines, the two groups starts to diverge. Typical readers begin to recognize the phonological pattern of the pseudo words and start recovering. Their fixation become more stable. But maybe because of dyslexic readers never find the pattern, each words remains equally hard. But however, more examination is required for the final conclusion of this one. But this is the pattern that we absorbed by analyzing the intrinsic explainability attention map. Also, I mentioned about a new metric called we introduced entropy for the measuring the reading regularity. So here high entropy means attention broadly distributed. So smooth regular reading, like the model has focused on most of the areas of the reading. So it means like a smooth and regular reading. But when low entropy means attention concentrated on the few fixation, maybe erratic or struggling reading. So when we compare the attention entropy values for the typical group and dyslexia group, we found that for the typical, it is a high entropy, and for the dyslexic, it is low entropy. The absolute difference is small. You can see like for the typical it is 4.61 plus or minus 0.54. For the dyslexic it is 4.08 plus or minus 0.65. The absolute difference is very small and groups overlap, but we have conducted a statistical significance test also. So the statistical results is strong. So entropy, so we can say that entropy captures the reading irregularity through the lens of what the model found diagnostically relevant. So this can be useful as a soft biomarker for a group level screening and tracking improvement over time with the intervention. See, like if it is high attention, we can say the attentions are broadly distributed. If it is low entropy, the attentions are concentrated, so they struggle with the reading. So let me discuss our what we found. What we found is like the two complementary tasks works better than one. When we combine the task 2 meaningful text and task 3 pseudo word reading, it captures the orthogonal aspects of the reading difficulty richer than either alone. And the second is about the intrinsic explainability compared to the post hoc explainability such as GradCam. So the gated attention weights directly governs aggregation, faithfully records the decision. Uh, so it can say like which fixation is more focused by the model to make the decision. And next one is about the efficiency advantage. We have captured just 10 features per fixation compared to the 400 aggregated features. However, we have to acknowledge multiple limitations because we consider only data from a single site and single language. So we can't say this approach is generalizable in all generalize everywhere. And also for the multitask fusion, we have just used a simple concatenate fusion after getting the embedding, multiple instance learning embedding from the each task. And also we haven't validated the causally validated the attention weight, because we should remember attention is not explanation, so further examination is required. So this is let me conclude our work. So this is the first multiple instance learning formulation for eye tracking based dyslexia detection, where we considered like a fixation level instance modeling, which can replace the globally aggregated features. Our multitask approach, gated attention fusion, achieves a 90% accuracy on a ETDD 70 data set, with providing competitive or surpassing all of the state of the art methods. And the intrinsic attention heat maps reveal clinically meaningful spatial reading patterns, so no post hoc explainability approaches are not required. And also about the new biomarker called attention entropy. So they are based on the statistical significance test we conducted. We can say like they are a statistically significant biomarker which distinguish the dyslexic group from the typically developing group. And the future work will be focused on cross language validation. Currently we have just conducted the framework evaluation only on the data set collected from Czech speaking students. So further focus will be on multiple languages. And also we have used a simple concatenated fusion for multitask. Maybe cross task attention based diffusion approaches will be implemented. And linguistic stimulus analysis is required, because currently our model has just understood like which words are or which fixation is important in diagnosing the dyslexia case or typically developing. Later we should find out the occurrence or frequency of words, like what type of words are this fixation, were these fixation maps to the which words are important for or feeling difficult for the dyslexia subjects. And also longitudinal intervention tracking can be another future works, because currently we are collecting the data from Qatar schools for the eye tracking. Not only eye tracking, we are collecting for eye tracking as well as EEG to create a multimodal data set. So we will further extend our frameworks to evaluate on other languages. So that's all. Thank you.
Thank you, Dr. Jayakant. We have time for one or two quick questions.
Yes, I'm not sure the presenter can listen to me.
Can you listen to the question on the audience, Dr. Jayakant?
Hello?
Maybe you have to come here.
Maybe.
Just a second, we have a question.
Okay.
I'm not sure it is here or it is in the computer. Yeah. Can you listen to me now?
Yeah, now I can hear you.
Yes. Congratulations on your work. It is very interesting. And we are starting to do something alike in a project in an institution I am at. to detect obesity problems, and we are also doing eye tracking. So I found your work very, very interesting. But I have a question. You found a new metric, the entropy. I'm sorry, I forgot the right name, but there is a single metric that allows me to identify dyslexia or not. And my question is, can you figure this metric without applying the eye tracking method? Or are you using the same T2 and T3 method to map out the entropy? Or are there other ways to figure out this entropy method?
Okay, so your question is specific about this entropy metric, right?
And how to calculate it?
Hello?
Yes,
Yeah, so your question is specific about this entropy metric, right?
yes,
Okay, so actually here we just introduced the Shannon entropy on attention weights because I already mentioned like we have the attention weights. Okay, so these are the attention weights that I have visually displayed. So
yeah,
this will show like which of the because we have a multiple fixation over the reading. I mean, for the reading task, we will have multiple fixation. You can see each one is a different fixation. So, based on our attention-based multiple instance learning model, it can tell us which of the regions are more focused by our model. Okay. So, based on this attention score, we computed the Shannon entropy.
yeah. So that is a Shannon. You just apply a Shannon entropy formula on the previous map.
Yes, yeah, we applied Shannon entropy on that one. Yes.
Thank you.
Okay. Thank you, Dr. Jayakant. I have a quick question, just to make sure you're treating dyslexia as a single class issue. Either you have it or you don't have it, right?
Can you please repeat the question?
Sure. From your slide, just a second. From your slide 4, you
Yeah.
are using a binary classification problem. Either you are dyslexic or not, right?
Yes, dyslexia or typically developing.
So there isn't gray areas or variants.
Yeah. Obviously, there can be like even inside the dyslexia itself, there can be different severity also.
Okay, I
Uh,
understand.
yeah, okay. But currently, we just focused on the publicly available data set, so which is already labeled by the speech, I think, occupational therapist. So they
Okay.
have already provided the labels like 35 subject is having dyslexia and 35 are typically developing.
I understand. Thank you very much.
Okay.
Thanks for your presentation. And I think
Thank you.
Eduardo is on the room. Can we
Yeah.
switch? Eduardo,
Hello.
Eduardo,
you hear me?
can you share your slides with us, please?
Yes, of course. I will share my slides right now.
Yes.
Just one moment, please. Everyone can hear my presentation? No, hear. No, see, sorry.
I can see your presentation, Eduardo. So the next presentation we have on this session of ICCSA is predicting temporal metrics in dynamic systems using machine learning. That Eduardo going to present. The co-authors are Saulo, Eder, and Alex. Eduardo, you have around 15 minutes to do your presentation, then we go for the questions. Is that okay?
Okay.
So please start when you're ready. Thank you.
Okay, I'll start my presentation. Good afternoon, everyone. Nice to meet you all. My name is Eduardo Marques, and today I represent the work, how I represent the predicting temporal metrics in dynamic systems using machine learning. So first, let's start by briefing contextualization the topic. So many real-world systems evolve continuously over time. Examples include epidemic spreading, communication in human contact networks, and information diffusion. In all these systems, interactions are constantly changing, so it's very important to us to understand when they occur. So this temporal information is essential for supporting decision making in many real-world applications. And modeling these dynamic systems is not straightforward. Science and networks change over time. Traditional static graphic models are not sufficient to represent these models. Instead, we use time-varying graphs or TVGs to represent them. TVGs explicitly represent interactions over time, allowing us to capture how the network evolves. This makes them a suitable framework for analyzing these temporal networks. So, formally, a TVG is defined by the set of vertices, edges, and time instants. And the key advantage of representing a graph as a TVG is the key advantage that every interaction is associated with a specific moment in time. This allows us to compare temporal metrics that identify important nodes and also reveal the most critical moments during the network evolution. And these metrics are particularly useful for planning interactions in dynamic systems. Now talking about the temporal analysis of dynamic networks, unlike the traditional static metrics, temporal metrics explicitly considered when the interactions occur. This allows us to characterize not only the structure of the network, but also how information or influence propagates over time. As a result, these metrics help us to identify the best moments for interventions, such as spreading information or controlling epidemic. In this work, we focus on two temporal centrality metrics. The first is cover time, or called CT, which measures how quickly a diffusion process reaches a given fraction of the network. And the second is time constrained coverage, or TCC, which measures how much of the network can be reached within a fixed number of times. In simple terms, CT measures diffusion speed, while the TCC measures diffusion reach. Here represent the formal definition of both metrics. Although the equations look complex, but the main intuition is very simple. Basically, CT tells us how long it takes for information to spread to the network, and TCC tells us how much of the network can be reached within a predefined time limit. These metrics are widely used for analyzing temporal diffusion processes. And however, there's an important limitation of using these metrics because computing these metrics requires a knowledge of filter interactions. But in practice, filter interactions are null and making them difficult to make a real-time analysis. And the existing approach usually try to reconstruct the filtered network topology before computing the metrics. So we have two problems here. Né? So we have asked two research questions. Can we estimate future temporal metrics directly, not reconstructing all the future network topology? And can we do this using only past observations? Our main idea of our proposed approach is to avoid predicting the future network itself. Instead, we directly predict the temporal metrics. So we treat each metric as a time series and use the machine learning models to forecast future values. This shifts the problem from predicting individual network connections to predicting aggregate temporal properties. And as a result, we finally estimate the future temporal behavior only using historical observations. So the slides summarizes your methodology. We first collected both real and synthetic data sets. Then we model them as a TVG. Next, we computed these temporal metrics and transformed them into a time series, where these time series were used to train different forecasting models. And finally, we evaluate the prediction accuracy using several error metrics. So here we evaluate our approach using two data sets. The first is the Monster data set, which contains face-to-face interactions collected in a hospital environment. It includes 160 participants and more than 4,000 temporal instants. And the second data set is a synthetic network with the same number of nodes, based on the Erdős-Rényi methods. And here Now we have the data set, we have to construct the time series. To perform the forecasting, we transform the temporal metrics into time series, where we transform the data sets into TVGs and finally calculate the centrality metrics. And but we have observed that only using time index was not sufficient to capture the underlying dynamics of the network, no, of the time series. So we adopted the lagged features methods to try to predict to the machine learning models try to predict the values. So in other words, the prediction of the next value depends on several prisms of observation. This formulation converts the temporal metric estimation into a standard supervised learning problem. So here in this equation, we have the time the time steps before of the machine learning model represented by k. And finally, we compare we evaluate our model compare with both linear and neural models. The linear models were linear regression and ElasticNet, and the neural models were multi-layer perceptron (MLP) and temporal convolution network (TCN). We also, I think that I want to ex, to clarify that we also evaluated several additional models such as ARIMA, LSTM, random forest, gradient boosting, and support vector machine. However, these models did not achieve competing performance results, and we do not include in the final comparison. So we only use it for models to forecasting. And finally, we have the results for the motor for Mosul dataset or the cover time metric. Here represent the results, and as we can see, the models closely follow the real values. And the prediction errors are extremely small. And among all the models, the linear regression achieved the highest accuracy with a error squared value very close to the to one and very low prediction errors. Here we have a monster dataset for TCC metric. Again, all models achieved excellent predictive performance, and all told, TCN performance is slightly better than the other natural model, that's the MLP, but linear regression still achieving the lowest overall error. These results indicate that temporal behavior of the Moser dataset is highly predictable, so the simple models can predict these results. And overall discussion for the Marshall data set is every model every model performs extremely well on the real world data. Surprisingly, the neural network did not improve meaningful advantage. And these results show us that simple linear models consistently achieving the best performance while they are easier to interpret and much faster to train. And here we have the results for the cover time for the random data sets. This problem is, as we can see here, this problem is considerably more difficult because the temporal dynamics are least structured. And as we can see, the prediction was increased for all models. Even so, linear regression and elastic nets remain the best performance model. And as we can see, the TCN showed the worst results. And for the TCC metric for the random data sets, we observe the same behavior. ElasticNet obtained the best overall performance, followed closely by the linear regression. And neural models remaining competitive but produce high predictable errors. And once again, the model complexity did not translate into better forecasting accuracy. And overall discussion for the random data set that compare with the most data set, prediction become more challenging due to the higher variability of the random network. In nevertheless, linear models continue to outperform the more complex neural approaches. And this suggests that temporal patterns are still sufficient regular to be captured using relatively simple models. And here, for overall discussion, compare both data sets reveals an important signs that the structured dynamics of the monster resulted in almost perfect predictions, and the random dataset was naturally more difficult to forecast. However, in both scenarios, increasing the model complexity did not improve performance. And instead, simple models like the linear one show lower errors, lower variance, and greater interpretability. And finally, to conclude, this work reformulated the temporal centrality estimation has a forecasting problem. Instead of reconstructing the future network topology, we directly predicted the temporal metrics from historical observations. And our experience showed that simple linear models consistently outperform us more complex neural networks. And for the future work, finally, we plan to investigate additional datasets, more temporal metrics, and a hybrid approach combining graph learning with time series forecasting. And I know it's a very fast presentation. I'm very nervous, sorry. So thank you all very much for your attention. I would like to acknowledge the support provided by the UFJF, Federal University of Juiz de Fora from Brazil, CNPq, FAPEMIG, and CAPS. And I will be happy to answer any questions.
Okay, thank you, Eduardo. Thank you very much. Questions? Actually, I have one question. Can you go back to slide number 12? You did a presentation okay. We're very quick. So, yes. What was the TCN data set again, the model again?
Oh, what?
The TCN model?
TCN is TCN model is the temporal convolution network.
It got very bad results. It just point. I noticed it was way large.
For the 12, or you see for the
for the MSC Mitrek.
Oh yeah. Right. Yeah, that's a very that's a very bad result here because but the to MSC because how you can see here for the Mozart data set, it's a very large data set as you can see now. He can move to 2015 to 5,000. So as we can see that the if MSCA metric is very bad, overall, as you can see here with TCN network, it's not follow very closely. I can zoom. No.
No, but we can get the idea. They're very similar. But the question, I was getting ready to ask you a question. You are a grad student, right? Masters?
No, I'm PhD student.
Okay, that's it. So I can be evil and ask you this question directly. Why so many metrics to evaluate models? That's something that in your final reading of your thesis, somebody may ask, why not stick to one and why use 6? It's a rhetorical question. You don't need to worry too much about answering that.
To be honest, my advisors suggest me to remove some metrics, but but I know that it's not needed. It's not necessary to R-squared, S-squared adjusted, and my MAPI and MSC root mean squared error. But for this work, I would like to analyze all the behavior on how we can see here, for example. Not always if you have a better model, it's all metrics we have better results. Okay. But for this work, I want to try to first analyze all the to prove that simple models outperform the complex models. I know that's not necessary to use all these metrics, but for this work, I try to use just to confirm that behavior, and I think that's it.
That's okay, though. Don't worry too much about it. I ask this when I'm sitting with the students, especially not my students, I ask a lot, why do you have 6 metrics? Why are you trying to measure? So what if they are different? It's just a rhetorical question, but it's a good practice to have this answer in the tongue of your tip, in the tip of your tongue. So why? Because I want to compare them. If we have a definite metric, nobody's going to use the other one. So I'm just yanking your leg. Don't worry too much about that. Congratulations on your presentation and good luck.
Thank you very much. Thank you very much.
Okay. And with that was our last presentation on this session. I will close the session and invite you Eduardo, if you have the time, join through Jitsi or YouTube to see all the presentations. We always learn something. Okay? So thank you very much. And then I close the session. Thank you, Eduardo. Thank you.
Thank you, guys.
Bye.
Bye-bye.
It was a pleasure. Maybe we meet at dinner.
Yes.